Hello, my name is Yoanh Espinosa. Thank you for visiting our presentation entitled Effective Property of Three-Phase Magnetoelectroelastic Fiber-Reinforced Composite by a Semi-Analytical Approach by Federico Sabina, José Antonio Otero, Héctor Camacho, Reinaldo Rodríguez, and myself. The knowledge of effective property of composite is important in application. Different models has been developed for the study of multi-phase composite in the wide field of problem. Therefore, they have been received great attention by research. Magnetoelectroelastic composites are a class of material that exhibit a maximum coupling between mechanical, electrical, and magnetic fields. They are made of piezoelectric and piezomagnetic phase. Also, they exhibit a remarkable magnetoelectric coupling effect that is not present in the constituents. This kind of material can be applied in devices of medical imaging, storage device, transducer, and magnetoelectric sensor. In this world, a semi-analytical method is developed to predict the effective magnetoelectroelastic property of three-phase periodic composite reinforced by unidirectional infinitely and concentric cylindrical fiber with a square transversal distribution. The present method is developed combining the two-scale asymptotic homogenization method and the finite element method. That is, from the asymptotic homogenization method, the analytical formulation of the local problem and effective property are obtained. Then, local problems are solved by finite element method via the principle of minimum potential energy. Its solutions are needed to find the effective property of the composite. General consideration. For the analysis, we consider a heterogeneous composite structure, defined as a three-phase magnetoelectroelastic fiber-reinforced composite. Reinforcements, fiber, and interface are unidirectional, infinity long, and concentric cylinders with different radii and material property. They are periodically distributed without overlapping in the homogeneous matrix. Also, constituents are assumed magnetoelectroelastic transversal isotropic materials belonging to crystal symmetry class C and M. The transversal cross-sections of the periodic circle Y consist of a square with two concentric circles of different radii R1 and R2, and T is the thickness of the interface. The static governing equation for magnetoelectroelastic composites, considering the absence of body for electric charges and electric current density, are defined by means of the homogeneous partial differential equation system on a media omega, together with the boundary condition on the omega surface. Here, the constitutive equations are defined by the relations, where the stress, electric displacement, and magnetic inductions are related with strain, electric field, magnetic field through the material elastic stiffness, piezoelectric, piezomagnetic, dielectric permittivity, magnetoelectric coupling, and magnetic permeability properties. These equations represent the fundamental problem associated with the linear theory of the magnetoelectroelasticity for a heterogeneous media. Also, the Cauchy relation and the electrodynamical equation for a quasi-static approximation are satisfied. In addition, a perfect interface or perfect contact between the phases are assumed. So, by means of the asymptotic homogenization method, the solution of the heterogeneous problem given by a classical elliptic boundary value problem with periodic and rapidly oscillating coefficients is found by means of the ansatz for displacements, electric and magnetic potential as a function of a geometric parameter epsilon, which represents a relation between the macro and micro scales, where the lowercase l is the distance between the centers of two neighboring fibers, and the capital letter L is the diameter of the composite. Then, an equivalent homogeneized problem defined in a homogeneous equivalent medio is obtained, where the matrix of effective properties can be found. For that, the local problem solutions are required to find the effective property over the periodic cell. Then, the homogeneized local problem over the cell are present in compact form by the differential equations subject to perfect contact conditions at the interfaces. Here, x, y, and z vectors are the known local functions to be found for each local problem over the cell. The preindex f is used to identify local functions, displacements, and potentials associated with the corresponding local functions, as can be seen in this table. Once the prescribed local functions are solved, the magnetoelectrostatic coefficients can be determined using the following formulas. Notice that the effective coefficients depend on the local functions by the expressions given here. So, the local problems can be solved by different methods, for example, via complex variable theory or using a semi-analytical approach using finite element method, which is the aim of the work. The semi-analytical approach here developed is a combination between asymptotic homogenization method and finite element method. That is, the local problem as solved by finite element method via the principle of minimum potential energy. The potential energy for a magnetoelectrostatic solid under perfect contact condition is written in a matrix form as follows. Here, the main idea is to find the local problem solution x, y, and z, which minimize the potential energy over 1/8 of the cell, 1/4 of the cell cross-section. This reduction simplifies the numerical computation. If we use the connectivity of the element, then the magnetoelectrostatic total energy is computed as a function of a shape function of nodal values. Once solved the local problem, the effective coefficients can be found. From now, a numerical example is shown. The following illustrations show the antiplane effective moduli of a three-phase fiber-reinforced composite with square periodic cell versus barium titanate BTO and cobalt ferrite CFO fiber volume fraction for different interface thickness T equals to 0, 0.01, 0.02, and 0.03. When the epoxy matrix is reinforced with either BTO or CFO fibers, the effective property have monotonous behaviors as the fiber volume fraction increase. The monotonous behavior can be related to the rule of mixture or the Voigt average. That is, if the inclusion property is higher, lower than the matrix ones, the effective composite property increase, decrease as the inclusion volume fraction increase. However, this rule is a linear behavior that is not observed in these pictures. The herein developed implementation with a fence consider also the physical interaction between constituents and the interface, which is responsible for the deviation from the linear behavior. It can observe that for low inclusion volume fraction, the increases of the effective property behave nearly linear. The support of these results can be seen in this reference. Thank you for visiting my presentation. My name is Yoanh Espinosa. See you soon.